In this episode, we look at technical architecture trade-offs, which are the choices you make when no design gives you everything at once. A system can be highly available, but that may require extra cost, extra complexity, and more monitoring. A system can be easy to use, but too much convenience can weaken access control. A system can rely on open-source components, but someone still has to track updates, review dependencies, and understand support limits. Architecture is not only about picking the strongest control or the newest platform. It is about understanding what the organization needs, what risks it can accept, and what responsibilities come with each decision. You are learning to think like someone who sees the whole environment, not just one server or one application. Good security architecture balances availability, resilience, compute capacity, power, recovery, usability, support, and operational responsibility. Before we continue, a quick note. This audio course is part of our companion study series. The first book is a detailed study guide that explains the exam and helps you prepare for it with confidence. The second is a Kindle-only ebook with 1,000 flashcards you can use on your mobile device or Kindle for quick review. You can find both at Cyber.Me in the Bare Metal Study Guide series. Availability means a system is accessible and working when people need it. If users cannot reach an application, if a payment system stops processing, or if a hospital workstation cannot access needed records, the system has an availability problem. Security often focuses on stopping unauthorized access, but authorized access matters too. A perfectly locked system that nobody can use does not support the mission. Availability depends on many things, including hardware, software, network connectivity, identity systems, storage, power, cooling, maintenance, and outside service providers. It also depends on design choices made before something fails. A single server running a critical service is easier to understand and cheaper to operate, but it may become a single point of failure. A more available design may use redundant systems, load balancing, clustering, or failover, but those features bring added cost and complexity that must be managed carefully. Resilience is related to availability, but it is not exactly the same thing. Availability asks whether the system is up and reachable. Resilience asks whether the system can absorb problems, keep operating in a reduced state, or recover quickly after disruption. A resilient design assumes that something will eventually fail. A disk may fail, a cloud region may have trouble, a network provider may go down, a patch may break a service, or a cyber attack may affect part of the environment. Resilience means the architecture has options when failure appears. That may include redundant components, alternate paths, backups, tested recovery procedures, graceful degradation, and strong monitoring. Graceful degradation means the system may lose some features, but continue to provide the most important ones. This matters because not every failure has to become a full outage. A resilient system is designed to bend before it breaks. Every availability and resilience decision creates responsibility. If an organization builds redundant systems, someone has to configure them, monitor them, patch them, test failover, and confirm that data stays consistent. If an organization relies on a provider's high availability feature, someone still has to understand how that feature works and whether it was enabled correctly. If a backup exists but nobody tests restoration, the backup may create false confidence. Responsibility is sometimes unclear in modern environments because internal teams, vendors, cloud providers, managed service providers, and application owners all touch different layers. A design can fail because everyone assumed another group was handling a control. Clear ownership is a security requirement. You should know who owns the service, who owns the data, who owns the recovery plan, who watches alerts, and who has authority to make changes during an incident. Compute decisions also shape architecture trade-offs. Compute refers to the processing resources used to run applications and workloads. At a basic level, this includes central processing unit, CPU, capacity, memory, and the platforms that provide them. Too little compute can make a system slow, unstable, or unable to handle demand. Too much compute can waste money and create more resources to manage. Cloud environments make compute easier to scale, but that convenience can hide cost and configuration risk. On-premises environments may provide predictable control, but they require capacity planning and hardware investment. Security tools also need compute. Logging, encryption, scanning, analytics, and monitoring all consume resources. If the architecture does not account for security overhead, teams may be tempted to disable controls to improve performance. That is a dangerous trade-off because the system appears faster while becoming less protected. Power and environmental requirements may not sound like cybersecurity topics at first, but they are part of secure architecture. Systems need electricity, cooling, physical space, and stable environmental conditions. A data center with strong access control can still fail if power is unreliable or cooling cannot keep equipment within safe limits. Organizations may use redundant power feeds, generators, batteries, or an uninterruptible power supply, UPS, to reduce outage risk. These protections cost money and require maintenance. They also need testing, fuel planning, replacement schedules, and physical security. In cloud environments, the provider handles much of the physical power and cooling responsibility, but the customer still needs to understand provider regions, service limits, and recovery options. In smaller on-premises environments, power may be a hidden weakness. A server room in an office closet can become a major risk if nobody planned for heat, outages, or safe shutdown. Recovery decisions turn architecture from theory into practical survival. Recovery Time Objective, RTO, describes how quickly a system should be restored after disruption. Recovery Point Objective, RPO, describes how much data loss may be acceptable, measured by the age of the last usable recovery point. These ideas help connect technical design to business expectations. A system with a very short RTO may need hot standby systems, automated failover, or active redundancy. A system with a very low RPO may need frequent replication or continuous data protection. Those designs are more expensive and more complex than occasional backups. Not every system needs the same recovery level. A public website, payroll system, identity service, customer database, and training archive may each have different requirements. Architecture becomes stronger when recovery choices are based on business impact instead of guesswork. Usability is another trade-off that security architecture must handle honestly. If a system is too hard to use, people look for shortcuts. They may reuse passwords, share accounts, store data in unapproved places, bypass processes, or delay important work. If security controls create constant friction without clear value, users may treat them as obstacles rather than protection. That does not mean every control should be removed for convenience. It means controls should be designed around real behavior. Multi-factor authentication, MFA, can greatly improve account security, but the user experience matters. A confusing approval process can lead to mistakes. A well-designed process can protect access without overwhelming the user. Good usability also helps administrators. If security tools are confusing, alerts are unclear, or routine tasks require too many manual steps, even skilled teams can make mistakes under pressure. Proprietary technology is technology controlled by a vendor that usually manages the product roadmap, licensing, support, and source code access. Proprietary products can offer strong support, predictable documentation, integrated features, and accountability through contracts. That can be valuable when the organization needs vendor assistance, guaranteed response options, certification support, or a product that works cleanly with existing tools. The trade-off is dependence. The organization may be limited by the vendor's pricing, licensing model, update schedule, product direction, and support quality. If the vendor changes features, raises costs, discontinues a product, or suffers a supply chain issue, customers may have limited options. Proprietary does not mean secure by default. The organization still needs configuration review, patch management, access control, monitoring, and exit planning. A trusted vendor relationship should reduce some burdens, not replace internal responsibility. Open source technology is software whose source code is available under a license that allows people to inspect, use, and often modify it. Open source can provide transparency, flexibility, community review, and freedom from some forms of vendor lock-in. Many security tools, operating systems, libraries, and cloud platforms depend heavily on open source components. The trade-off is that visibility into code does not automatically mean someone in your organization has reviewed it. Community support can be strong, but it may not provide the same response guarantees as a paid vendor. Open source projects can also become abandoned, undermaintained, or dependent on a small number of volunteers. Security teams must track versions, vulnerabilities, dependencies, licenses, and update paths. Open source can be an excellent choice, but it still needs ownership. Someone must know why it is used, where it is used, and how it will be maintained. Dependency risk is especially important when using open source components, but it can affect proprietary products too. Modern applications often rely on many libraries, packages, modules, and supporting services. A developer may add one helpful component, and that component may depend on several others. This creates a chain of trust. If a dependency has a vulnerability, is maliciously modified, or is no longer maintained, the application may inherit that risk. In architecture, you should think beyond the main product name and ask what it depends on. Software composition, update processes, source integrity, and package management all matter. The same idea applies to vendors and providers. If your system depends on a cloud service, identity provider, payment processor, or managed security platform, their outages and weaknesses can become your problem. Architecture trade-offs include not only what you build, but what you rely on. Complexity is one of the quietest technical trade-offs. A highly available, highly resilient, feature-rich architecture can become difficult to understand. More components mean more configuration, more permissions, more logs, more network paths, more failure modes, and more people who need training. Complexity can hide risk because nobody can easily see how all the parts interact. A simpler design may be easier to secure and operate, but it may not meet availability, scalability, or recovery needs. The goal is not to make every system simple at all costs. The goal is to avoid unnecessary complexity and document necessary complexity clearly. You should be able to explain what each component does, why it exists, what happens if it fails, who manages it, and how it is monitored. When a design becomes too complicated to operate safely, complexity itself becomes a security weakness. Trade-offs also appear between standardization and flexibility. Standardization means using approved patterns, common platforms, known configurations, and repeatable processes. It helps with training, monitoring, patching, troubleshooting, and audits. Flexibility allows teams to choose tools that fit special needs, adopt new technology, or solve unusual problems. Too much standardization can slow innovation and force poor fits. Too much flexibility can create sprawl, inconsistent controls, and support problems. Architecture should define where variation is allowed and where consistency is required. For example, an organization may allow teams to choose different development frameworks, but require standard identity integration, logging, encryption, and backup patterns. This kind of balance supports both security and productivity. The strongest designs do not demand sameness everywhere. They identify the controls that must be consistent and leave room for thoughtful choices where risk is lower. A technical architecture decision should always connect back to business purpose. Availability matters because people depend on systems to work. Resilience matters because failure is unavoidable. Compute and power matter because applications need real resources to run. Recovery matters because disruption has cost. Usability matters because people must be able to use controls correctly. Proprietary and open source choices matter because they affect support, transparency, flexibility, cost, and responsibility. The right answer depends on the system's role, the data it handles, the users it serves, and the impact of failure. A small internal tool may not need the same design as a public payment system. A safety-related system may need different priorities than a marketing website. Security architecture is strongest when technical choices reflect the value and risk of the service being protected. Technical architecture trade-offs are not signs of weakness. They are the normal reality of designing systems that must work in the real world. You cannot maximize availability, resilience, usability, control, flexibility, simplicity, and low cost all at the same time. Improving one area often adds pressure somewhere else. More redundancy may increase availability, but also increase complexity. Stronger controls may reduce risk, but create user friction if they are poorly designed. Open source may improve flexibility, but require more internal ownership. Proprietary tools may improve support, but increase vendor dependence. Strong recovery targets may reduce downtime, but raise cost. Your job is to recognize the trade-offs instead of pretending they do not exist. A secure architecture is not the most expensive or most restrictive design. It is a design whose choices are deliberate, whose responsibilities are clear, and whose risks are understood before failure tests them.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.